Hello, this is Terry Kuzma here at Penn State University. And what we're doing today is we're going to take a look at other characterization techniques that are used especially in bottom-up manufacturing, or some that could be used in that area. And this is part 2 in our series. And what we're going to take a look at today is the scanning helium ion microscope and magnetic resonance subnanometer imaging. So again, this is where we are in our outline. So let's take a look at the scanning helium ion microscope. So people call this shim or shim's technique. It's similar to a conventional SEM, but what shims offers is increased sharpness with a larger depth of field on a wide range of materials. So shims uses a short de Broglie wavelength of helium ions, which is inversely proportional to their momentum. So we can take a look at this at this equation. So we can see that the wavelength is equal to Planck's constant divided by the momentum. So shims has a very small wavelength due to the very low momentum of the helium ion. So shim shares the ability of ion systems that allow system sample milling and adding observation to levels that are to sub-nanometer resolution. Compared to an SEM, the secondary electron yield is high, allowing for imaging to occur with currents as low as 1 femtoamp. Recall that secondary electrons provide topographic information in the SEM. This will result in an image that shows all high and low points of a sample in greater detail and at the same time in greater focus. So the sample's damage is very, very low if we would select helium as our ion source. And in shims, we can actually select multiple ions or to do our interrogation. But for at this time, what we're doing is using our building our conceptual model here using the helium ion source in the system. So the detectors provide information-rich images which offer very good topographic, material and crystallographic and electrical properties of the sample. And we can see this in our cartoon here at the lower right-hand side, that we have this helium ion beam. And basically what it does is it gives us a narrow interrogation spot where we have in the SEM with the electron beam, we have what's referred to as, I guess, straggle, the blooming of the electrons at the interaction of the material. So electron beams have a large scattering effect and interact in a broad area. This causes emissions and secondary electrons from an area that's larger than the beam size. So again, what this is going to do is give us, in some senses, a false picture of that particular area, because we're getting this imaging or archive or other attributes of the blooming from the interaction. But with the smaller beam spreading of the helium ions, we're able to get a better, more resolution from the sample. So helium ions are about 7,000 times heavier than electrons, and neon ions, which are also another possibility as a source in the system, are 40,000 times heavier than electrons. Because of this, helium or neon exhibits very little diffraction when passed through the aperture or across the edge. So we can see this in our picture here on the right, where we have the more spreading with the electron than we do with the helium, and even more with respect to the neon ions. So non-conducting samples can be problematic without metallic coatings, as when we compare this to the SEM process. Since the impinging ion is actually positive, it is possible to build up positive charge on the surface, but this can easily be overcome with an effective electron flood gun, which would keep us at neutral polarity on the surface, and per se would make the resolution of the detector easier to see. So this means that that it's not necessary to coat the sample with a conductive material, and that material could potentially obscure the imaging. And typically in an SEM, to bleed off electron charge, we would use either carbon or gold. They're the most popular. But again, since we don't have that issue here with shims, we don't need to have those coatings on there. What we would do is basically an electron gun. So the helium microscope offers a larger depth of field, and this depth of field can be as much as 5 to 10 times as much as compared to a typical high-end FESEM. So this is, I think, one of the better systems on the market from my research of the literature. It's the Zeiss Orion 30. It's commercially available, and it's capable of imaging of about 0.5 nanometers. In addition to the imaging capability, the system can also perform etching, deposition, and lithography. So this can act as a focused ion beam and do chemical deposition and lithography at the same time. So it actually has a lot of utility as a tool. So the Zeiss system features 3 beam sources for material processing. This allows adjustment of beam current, beam energy, and importantly, ion mass. Its uses include material removal using sputtering, gas-induced etching, or deposition or lithography. The gallium FIB is used to remove relatively large amounts of material, so this beam could potentially contaminate the material. So again, we can have these multiple beam sources, and what they're going to offer us is, with helium, we don't have that much kinetic energy on the surface, so our sputtering would be at a minimum. But when we would select other beams that have a larger mass in the ion, they would give us more kinetic energy and offer us the ability to do sputtering, and or they could chemically interact with the substrate, giving us potentially some deposition. So neon beam, which has a larger mass than helium for precision nanomachining, offers speed that the helium beam can fabricate delicate sub 10 nanometer structures. Having more kinetic energy, neon can resist faster than helium. Gallium has even more mass and can be used for rapid prototyping and for larger feature sizes. Naturally, helium and neon will provide less contamination because they're noble gases than the gallium interaction. And so what we're doing is we're training off all these parameters, such as the kinetic energy, the speed to do the process, damage to do the process, and chemical contamination from the sources such as gallium. So again, that's why there's multiple beams on the source. Depending on what work you need to do, you can select the ultimate beam ion for that particular application. So the Zeiss Orion NanoFab features nano patterning and visualization energy. This is an integrated hardware and software controlled system. Software is capable of creating a range of fully editable shapes, including rectangles, trapezoids, polygons, lines, polylines, ellipses, and spots. Vector fill these shapes while maintaining full control over dose variation and patterning. So this system, I think, is very cost effective because you can make these per se direct writes on the surface, or make masks within this tool. So it's a very useful tool. So again, what I'd like to do is continue our presentation at this point, and what we're going to do is shift gears and take a look at magnetic resonance sub-nanometer imaging, which is a rather eclectic system, not used in a number of places. So this is more of a research tool. So we're going to look at this from the I guess, a perspective of what's possible in imaging, and a review of the physics, some interesting physics here. So magnetic resonance sub-nanometer imaging tool, it's a conventional magnetic resonance imaging, is limited to spatial resolution in the micrometer range. But with magnetic resonance sub-nanometer range, the imaging is capable of detecting weak magnetic forces from nuclear or electronic spins. This method can provide information of the nanometer and possibly the atomic scale ultimate resolution is single electron spin sensitivity. So the MRFM combines the ultrasensitive force microscopy with the resonant imaging, with magnetic imaging techniques. So the principle for this application: a sample containing nuclear spins is attached to an ultrasensitive cantilever and brought into close proximity of a nanoscale ferromagnet. The resulting magnetic force slightly deflects the cantilever, measured by a laser interferometer. Radio frequency pulses are used to modulate the nuclear spin magnetation and to create an MRI signal. Scanning can produce 3 images of the sample. So basically, this technique works by measuring the response of nuclear magnetic moments, or the spins, of a sample to external magnetic fields and to controlled electromagnetic radiation. So this shows our diamond tip, and this gives us the repulsive force that is in repulsion, or acts against the spins in the sample. So this shows us our diamond tip. So this defect in here actually gives us this point vacancy defect in the diamond lattice, gives us this magnetic moment within our probe tip. So the diamond defects carry a spin that's very sensitive to magnetic fields. The optical rate of emission depends on the defect spin state, which can measure small fields by simply looking at the fluorescence intensity. So this shows us a schematic of the system that they have at the MIT lab. And again, this is basically a research tool. I don't think that there's many of these exist around, and I don't think that these are, at least at the time of this presentation, are commercially available. This is basically systems that are made on site by researchers, but they're able to resolve these spin states down to a high level. So these nitrogen vacancy centers emit bright red light and can be conveniently excited by visible light sources such as argon, krypton, helium, neon, and other lasers. At room temperature, no sharp peaks are observed because of the thermal broadening. However, cooling the nitrogen vacancy centers with liquid nitrogen and liquid helium dramatically narrows the lights, narrows the emission lines down to a few megahertz width. Transitions between the triplet ground state of each excited state can be individually addressed via resonant optical excitation. So this shows us the mixture of these different types of techniques. So again, like we interrogated in the TRS, which was basically the AFM and the SERS merged. This is the magnetic MRI type of application merged with the AFM. So again, this gives us this small resolution and small spots size due to the enclosure of the diamond on the end of this tip. So that, again, you can take a look at this schematic provided to us by MIT. So again, this shows us actually the interaction of the incoming microwaves, which match the resonant condition, and the diamond vacancies, which provide the repulsion in the system. And again, here's some further look at the laser pumping of this interaction of the system as it goes across material. And I guess that material might be DNA in the interrogation of the system. So I guess this is a pretty interesting system. Basically, they do this in vacuum because they don't want, between the tip and the sample, they don't want other stray atoms or molecules interfering with the process. And we can see that this image height in this area is about 5 centimeters. So this is basically the setup here at MIT. So these, they can look at some achievements that they've published here. They can detect single electron spins, and they have detected single electron spins in 2004, and they have been able to show this magnetic resonant imaging of nanoscale biological samples since 2009. So again, these advantages include possibility of site-specific image contrast, absence of radiation damage. A single copy of an object is required. This is well suited to provide structural information of large biomolecular complexes that are known to overwhelm other larger scale nuclear magnetic resonance systems. The disadvantages include identifying a specific area. These also can include gas in proximity of the probe, so that's why they would like to use this in a vacuum system. Naturally, this is a detailed test to look at small areas, so it is very time consuming to interrogate large surfaces. So that was a brief look at our three different characterization tools that we took a look at in this class. I think they were interesting, and certainly the first one and the last one was pretty interesting, that we see the utility of the AFM. So I do think that a conventional thing that people do with AFMs now, they measure other scientific techniques with the AFM to give a smaller spot size. So I think that there's probably something like 60 different types of techniques that you could do with a standard AFM configuration. So it's a large area of research. One of my colleagues actually recently left Penn State to do research and sales with an AFM company, and he said that the work is very broad and interesting. So it is a nice area to look at. So again, this is some examples that show that potential. So thanks for tuning in and paying attention during this discussion on a characterization for bottom-up materials. I hope you've enjoyed this series, and maybe a little bit of apologies, because during my recording of this class, I've had a pretty bad cold, so I hope that my voice has been okay and I didn't cough that much. All right, guys, take care. We'll see you the next time, and hope you enjoyed this, and we'll look forward to doing some more research and discussion in nanotechnology. Take care.